Imagine waking up tomorrow to a city that has stopped. The power grid goes dark, your smartphone is a dead brick of glass, and the computers running everything from water treatment plants to hospitals simply shut down. This total collapse is prevented by a mechanism hidden deep inside the microscopic architecture of crystals. Welcome to solid-state physics. This is the science of rigid matter, examining how the incredibly dense packing and interaction of atoms dictate every physical property an object possesses. Common window glass has atoms scattered in a chaotic, irregular arrangement. This makes it an amorphous solid. Metals and ordinary ice, on the other hand, feature atoms that lock into highly ordered, repeating geometric patterns. To understand the modern world, we have to look past the macroscopic machines we use every day and examine the geometric arrangement of atoms that gives them their function. That ordered pattern is called a crystal lattice. Think of it as a repeating three-dimensional blueprint built from a basic unit called a primitive cell. This diagram shows how scientists navigate this microscopic architecture. They use a mathematical coordinate system called Miller indices to map out exact planes and directions within the grid of atoms. Take the element carbon. Depending on how you arrange its lattice, the exact same atoms produce completely different materials. They form flat sheets of graphite, the dense tetrahedral interlocking of a diamond, or a spherical buckyball. These structural differences change how electrons are shared between atoms. One geometric arrangement creates a conductive metal, another builds a rigid electrical insulator, a third forms a superconductor. For early physicists, the logical conclusion was clear. If geometry dictates physical power, then engineering a mathematically perfect, flawless crystal would yield ultimate control over technology. A mathematically perfect crystal is completely inert. For modern electronics, it is virtually useless. Solid matter becomes technologically useful when it is flawed. We get our most valuable materials by introducing what physicists call point defects. One of the simplest imperfections is a shock devacancy. This occurs when an atom is completely missing from its designated spot in the lattice. That empty hole gives other atoms room to move and diffuse through the solid. Materials also contain larger structural flaws called dislocations. Here, entire planes of atoms become tangled and misaligned within the crystal. These chaotic lines dictate the mechanical strength, flexibility, and malleability of everyday metals. Perfection is rigid. Deliberate imperfection provides the exact levers scientists need to manipulate a solid's behavior. To use those levers, we have to shift our focus from the static atomic grid to the electrons trying to navigate this flawed landscape. This animation shows how overlapping atoms cause electron paths to smear into distinct zones, called a valence band and a conduction band. They are separated by a strict boundary known as a forbidden energy gap. In an insulator, that gap is too wide for electrons to cross. In a conductor, the bands overlap, allowing electricity to flow freely. Semiconductors, like silicon, sit right in the middle. They have an energy gap that is small enough to be manually overcome. We overcome it through a technique called doping. By intentionally injecting foreign impurity atoms, like phosphorus, into a pure silicon crystal, we manipulate the flow of electrons on demand. This deliberate doping allowed physicists like William Shockley and his team to invent the transistor. This microscopic gateway controls electricity with absolute precision. It serves as the foundation for memory bits, logic gates, and the processing power of modern computers. Humanity gained mastery over electricity and built the digital age only after we abandoned the pursuit of the perfect crystal and embraced controlled flaws. At the deepest levels of solid matter, standard macroscopic physics is replaced by the wave-like rules of the quantum realm. Take the concept of a hole in a semiconductor. When an electron moves, it leaves behind an empty space. In solid-state physics, the physical absence of that electron behaves exactly like a real particle, complete with its own mass and a positive charge. Mastering these bizarre quantum behaviors between electrons and holes pushes material science to its absolute extremes, leading to phenomena like superconductivity. Without superconducting materials, we could not generate the massive magnetic fields required to keep MRI machines functioning in hospitals worldwide. Now, researchers are engineering single layers of atoms, like graphene. These structures provide the architecture for neuromorphic chips that mimic the human brain and for the logic gates of quantum computers. Solid-state physics is the ultimate act of modern alchemy. We didn't passively observe the perfect atomic structures of nature. We learned exactly how to break them to build the modern world.